Hello class, this is Dr. Viv again. I thought I'd make yet another video on moments of inertia because the previous example came out to be that of a uniform rod. So here's another one. Let's try an example where you still have the rod pivoted about its middle. So the left end is at negative L over 2 and the right end is at L over 2, and it's pivoted at x equals 0. That's your y-axis. The basic setup is the same in these problems. You take some mass element, and just for change I'll take it on the left side to show you there's nothing mysterious about left versus right. That's the distance x, and let's just say that it's got a mass distribution which happens to be something like this: lambda of x equals bx squared. Now for the sake of making physical sense of this mass distribution, we will take b to be positive, because negative mass is not quite understood. Let us now remember what lambda is. It's the rate of change of mass with distance, so that tells us that dm can be written as lambda dx. And what I'll do next is to compute the moment of inertia of this rod. The moment of inertia, as always, is given by this formula, which is actually found in your formula sheet, so I thought I'd expose you to that way of thinking about it. It's just the moment of inertia definition for an arbitrary distance r from the axis of rotation. Now in this case r is equal to x, so in this example r is equal to x. So I'll write this as negative L over 2 to positive L over 2 x squared dm, which is lambda dx, and lambda is bx squared. Now we'll evaluate this, bring the b outside since it's a constant. Integral x to the 4, which is x to the 5 over 5. And well, that's going to be just b over 5, and then the upper limit is L to the 5 over 2 to the 5, which is 32, and the lower limit is negative L to the 5 over 32. And that works out to be b over 5 times L to the 5 over 16. I'm just going to leave it like that, not simplify it any further. Let's next find the mass. Remember, our goal is to express everything in terms of the rod's mass. The mass is given by integral dm, and that is the integral from negative L over 2 to positive L over 2 bx squared dx. So this is bx cubed over 3. And that would be b over 3 times L over 2 cubed is L cubed over 8 minus L cubed over 8. So that works out to be b over 3 times L squared over 4. Now let's express it in terms of mass. Iy is, now you have this b over 5 here and b over 3 here. So what I'm going to do is I'm going to compensate for that by writing this quantity in a special way. I'm going to write Iy as 3 times 3 b over 5 L to the 5 over 16. I've done nothing illegal because 3 over 3 is 1, but now I have an opportunity to move the 3 under the b, and so I'll do that. I'll trade the 5 and the 3, and I'll also appropriate, because I need L squared over 4 for making the mass, I'll appropriate that L squared over 4 from this factor, leaving us with that's L cubed. So that's L cubed over 4, leaving us with L squared over 4 here. So that's just the mass. I'm going to write this as and that's 5 times 4, which is 20, 3/20ths ml squared. The standard result for a uniform rod would be I uniform is 1/12 ml squared. So if you had a uniform rod of mass m pivoted in the same fashion as this rod about its center, then that uniform rod would, the degree of difficulty to rotate that uniform rod would have been 1/12 ml squared, whereas this is 3/20th, and you can clearly see that 3/20th is bigger because it's approximately 1 over 7, since 7 times 3 is 21, and 21 and 20 are close. So that's 1 over 7, and that's 1 over 12. So this rod is going to be harder to rotate, and it's pretty obvious why, because you can see that this mass distribution tells you that there's more mass on this side and this side compared to in the middle. The mass density is exactly 0 in the middle, so it's a pretty lightweight center. It's got very lightweight center, and then as you go further out it becomes heavier. So if you actually plot the lambda function, it looks parabolic. So this lambda function, that's your lambda of x, you can see that it increases quite a bit as you go out, and so that accounts for the increased moment of inertia. Alright, thanks for watching.